So welcome to the Tartan SLAM Seminar Series. And today it is my great pleasure to introduce Wolfram Burgard as the speaker. So let me give a brief introduction. And if I would do a full introduction, half of the time would be gone for his talk. So Wolfram is a professor at the University of Freiburg in Germany. He's heading the Lab for Autonomous Intelligent Systems. And he was also recently vice president for machine learning at Toyota Research Institute. So Wolfram got his PhD in Bonn in 1991. He also has a close connection with Carnegie Mellon University. He was actually a research fellow here in 2002, and then adjunct faculty. And he's really well known in robotics. He wrote 2 books, one of those probabilistic robotics that most of you are probably aware of. He's a fellow of IEEE and AAAI. And in 2009, he received the Leibniz Prize, which is the highest German research award. So that in that, not just in robotics, right, but overall areas. So his work is generally on mobile robots. And some of the highlights include the Minerva robot, in the Smithsonian Museum of American History in 1998. So there was a robot that could show around people. More recently, Obelix in 2012, an autonomously navigating robot in pedestrian areas, so outdoors. And so today, he's gonna focus more on autonomous driving. Right, so Wolfram, please.
Yeah. Thanks, Michael, for the kind introduction. And yeah, it's really great to get back to CMU also. Unfortunately, I'm unable to do this in person today, but it's always a great pleasure to be there and talk to people. It's a great place to be. So today I'm going to talk about probabilistic and deep learning techniques for robot navigation and also autonomous driving. I will start with mostly navigation, robots, and then at the end of the talk go more towards navigation. And then throughout this talk, I will basically show what we accomplished with all these probabilistic approaches that Michael is also a pioneer in, and then ask the question like how we can go further, right? How can we go beyond this? And this is a discussion that I actually want to start, and maybe something that I think we should look in more deeply in the future. So what are, from my perspective, the key challenges in navigation? And when you look at applications like logistics or self-driving cars, right, you basically are interested in like highly accurate localization. This is basically one of the key challenges that we are having, right? And particularly with autonomous cars, like one of the tasks that they need to do is to stay on the road, meaning they actually need to be able to understand exactly where the lanes are and accurately stay in the lanes. But the same is true also for robots navigating factory floors. And in order to achieve this, we want to have robust mapping, right? That, I mean, usually our SLAM or navigation solutions work in the way that we first build a map and then we use this map for navigation and localization. But that opens this question: how can we actually establish long-term autonomy? And that is it's basically the 2 ends of the spectrum that we are in. And this is what the talk also today is about. But I will first start with localization and SLAM technology and how far you can actually get with nowadays SLAM techniques. We all know particle filters for localization, and you here see this famous video where you basically see a robot figuring out where it is in the world, right? So this is a piece of math that is well understood, and we have a couple of algorithms for doing this that are extremely robust and that can actually allow robots to accurately navigate. But the question is, how accurate are these algorithms? How accurate can we get? And given the map that we see, right? So, and here is an example of a robot on a factory floor that uses its LiDAR range scanners, these yellowish devices here in both corners to localize, and these black stripes here on the ground are simply used to demonstrate how accurate this is. And when we made these experiments and we used the motion capture system to basically figure out the ability to localize, right? Then the accuracy in localization, then we figured out that the localization accuracy was higher than the positioning accuracy. Basically, the robot actually knew that it was off the position it was supposed to be, but the controller actually didn't allow the robot to get there anymore. Which means that like we are extremely good in localization. And here is the very same with the 11-ton vehicle that is actually supposed to, like in a larger fraction, supposed to in a larger version, supposed to transport fuselages of airplanes. And here you can see that in the static setting, like we are actually, when it comes to the translational error, in the millimeter range, right? Even when we introduce changes with these wooden structures here and disturb larger parts of these scans and make them deviate from the map that the robot actually uses. So that means that we can actually provide highly accurate localization, but we can also go cheaper in the sense that we can do this, for example, with cameras. And this is a paper that I worked on together with some of my students, Tim Kaselitz, who just graduated, where we basically try to localize a camera based on 3D point clouds. And so the idea of this approach is to take an expensive sensor, generate an accurate point cloud, and then use a cheap camera to perform localization. And this is basically done by using sequences of or reconstructing 3D points based on SLAM in this case, right? And then calculate the 60 camera pose using ICP and nonlinear least squares. This is basically the key idea. And and here you can basically see the camera points projected onto the LiDAR scan based on the Kitty odometry data set. And we also have a data set created for like our campus in Freiburg, who wasn't at RSS. Like you will now see a small video of the campus in Freiburg where we had RSS, where we basically calculated a 3D map beforehand and then localized the camera in this relative to this 3D map. And here are the accuracies of these runs with two different cameras. And right, so and this is basically here now the video showing like on the left-hand side how you're basically estimating the pose of the camera, and we are even colorizing the model or the point cloud. The fact that some of the trees are bluish is because of the differences between the average color that we get from the pixels, which are basically pointing towards the sky and projecting them onto the branches of the trees. So this is why the trees look like light blue or have a light blue cloud color. Right? So we can even go to cheap sensors once we have the corresponding geometry and localize cheap sensors at a high accuracy. Right? And then you can also do this like for example, with autonomous cars, like in valet parking. This is work that goes back to Dirk Handel, who is now at Waymo, and working on self-driving there. And this is basically things that we can now realize using modern SLAM technology. But one of the arguments, okay, let's first go. You also do have solutions for SLAM, and I guess I can also go only quickly over calculating these maps and quickly go over this. This is the standard graphical model for SLAM, and here we have particle filters that are a solution towards that, or optimization approaches. And Michael is a famous roboticist in SLAM, and in particularly in graph-based SLAM, where it is basically optimization approaches for calculating the most likely map. And basically, this is the underlying equation that we use in the SLAM is an optimization problem. And then you can have different versions. Here, this is sparse post adjustment, where you can do this on the fly, not while the robot is moving, or you can do this in a batch version, where you basically calculate the most likely map retrospectively. This shows basically the graph and the optimization process, and then can also go wild and initialize everything with 0, 0 and a random angle, hoping that this map unfolds to the correct one. Depending on the initialization, we all know it can get stuck in local minima very well. This is where we are with respect to mapping itself. But now we have this problem that there might be changes or the dynamics. But before we go to this, let me quickly refer to like a work that has been done by a startup that I'm involved in here, and taking this to the extreme, basically, using it in a commercial fashion. And .scene is concerned with basically calculating maps of real estate and buildings for example, cultural preservation. And they recently went to a famous place and created a map for this of this building. And I will just let this video run in order to give you an impression of like what we can nowadays do with modern SLAM technology. .scene uses a specific sensor head that they take into the building and also mount to a drone, and they fly over the buildings and optimize both the interior and the outside of that building in one approach. And you can basically see the staircases that they went up, and at the very end, like see also the entire full building. Yeah, and then we do a virtual fly over this building, right? The Leaning Tower in Pisa. It's one of the most accurate models that they are having right now, and it's really cool. Like in the end, when the virtual flyover goes under the ground, where you can then basically see how the basement of this, how inclined the basement of this tower already is, so to basically monitor the structure or the building itself, and also other aspects of it, like the angle and so on and so forth. So that would allow you to basically monitor also changes in the building. And here you can see like how inclined this building actually is. Here we do have the Freiburg Cathedral. This is actually one of the most accurate model of that building that we are having right now. So there's actually also commercial applications of SLAM technology outside of robot navigation. But the problem is now that we do want to work with these maps, right? Or if we want to work with these maps, then we are always restricted, or we are concerned by these changes in the environment. And particularly when you think about cameras, then that means that we do have varying lighting conditions, right? So basically, very, very many approaches are like prone to errors when we change the lighting conditions, right? Features don't work anymore, or like dense approaches like are basically not working as hoped anymore. So dealing with varying lighting conditions is an extremely challenging aspect, particularly when it comes to, like, for example, localization, camera-based localization. And this is work here that I'm going to present this with that we did with, or it's mostly done by Tim Kaselitz and Michael Krawitz, and Michael is also in this meeting here. So if you have in-depth questions to this part of the talk, then just ask Michael at the end about like how this works and whatever you want to know about this. So Michael will be happy to answer this. So what is the idea here? All right, so think about this room over here in which you want to like track your camera while navigating through it, right? And if you introduce lighting changes, then we all know that this might be extremely hard. So if you go for a feature-based approach, then all of a sudden, like the features do not correspond to each other anymore, and you will encounter problems with the position estimate of the camera or the tracking process. So there is actually one. The idea is basically look at the reflectance of all the points in the model, right, which are supposed to be invariant to the illumination, right? And reflectance is basically the radiosity divided by the irradiance, right? So if you estimate radiosity and irradiance, we can calculate the reflectance, and out of this, then maybe get some lighting invariant representation that we can use for better tracking cameras. So this is how this pipeline basically works, right? You first calculate a 3D model, then do a geometry reconstruction, estimate the radiosity, and do some light source segmentation and the irradiance computation, and then we calculate the reflectance. So this is basically depicted here on the right-hand side. So geometry is done in a pretty standard way, right? So we are using SLAM, like the RGB and depth images, basically to calculate the poses of the camera, the truncated sine distance function to calculate using marching cubes to basically calculate the surface of the triangular mesh representing the environment. Right, and this is like the representation of this room that we just saw, and so and that's basically SLAM, right? As we with distance data, right? But we are now in this process where we actually do want to estimate also the color and being able to using RGB values for tracking the camera. And for this, we basically need to calculate the radiosity, which you can see here, right? And the next step basically is to calculate the irradiance, right? And once we did this, right, we basically get something like, or do this, we get a model out of this, like this one over here, right? So this is radiosity and irradiance. And then we know, right, that by dividing radiosity by irradiance, we get the reflectance. And as I mentioned, this is supposed to be independent of the illumination. Or mostly. So, and so, for example, here you can see that even if you substantially change the lighting conditions, so what we have here is now like this, from there to there, this light over here is switched off, right? At least this is the one that you can see, and probably other ones as well. So we get different irradiances, right, as well. And then by subdividing those, we get almost the very same reflectance. So what is interesting here is, for example, that shadows are not that present anymore or hardly visible, which is basically that's what we actually want to have, because the shadows are generated by the illumination, right? And so of course, right, the problem with this is now, like, ideally we could use directly these reflectance maps for localization, but the problem is that this entire process, or this pipeline that I showed, is too expensive to actually directly perform this on these reflectance maps live or online. So here, what you can see here is the resulting reflectance depending on the lighting settings. So we only have like a red, a green, and a blue lamp here, and these are the resulting reflectance. And then we did some experiments basically showing how the reflectance values differ depending on the original lighting that we were having. Right? And from these values, you can at least see that they're relatively similar. So which means that this process in principle works well. So the next step is that we also estimate the light emitters, or the light, simply by looking at the intensities. And right, so once we have those, right, we can now play around with these light emitters and adapt or calculate, really render the scene using the resulting maps, and then basically render the scene depending on the configuration of the individual lights. So this is pretty cool, and that is the idea now, basically how to use this for localization purposes. So the key question is now how to basically calculate the light contributions of the individual lamps. And this can be pre-computed. And then, so for every lamp, so we basically calculated for every lamp, the contribution, and then compose the contribution for a given light setting in real time and on the fly. So instead of like doing this entire pipeline for every image, what we do is we basically calculate the contributions of, or use these models that we're having right now to calculate the individual contributions of the lamps, and from that calculate the scene depending on the lighting configuration, which then allows us to quickly compare this to the image that we actually get. Right? So here is the scene depending on, so the lights are covered by these red patches here, which is why this is hard. And what you see were basically different lighting settings of this. And this plot basically shows how much like iterations you need to do, or how much ray tracing you basically do in order to achieve like, or approximate the optimal, or to minimize the difference between the observed images and that what you generate by this rendering process. And here, for example, you see this for k = 0, right? So if you do like 1 bounce for every ray, then this is what you get as a result. And 2, and then for 10, it is almost basically the very same. On the right-hand side, you basically see the real picture projected onto the mesh. So what, the outcome. A very interesting aspect of this project basically also was that we had sometimes had problems to get papers accepted simply because people said, hey, the images that you generate are like cannot be distinguished from the actual images that you perceived. And it's kind of like a funny side note on this project. And and then you can basically use this also to switch off lamps on the fly. Here for a different scene. And now you can basically use to exploit the lighting during the camera tracking in the room. And this is done in the following way, right? We are basically like, we estimate the light setting, right, based on our observations. And then given the light setting, we render the image and then track the camera based on this rendered image. And so which also means that we can on the fly adapt to the changes in the lighting, right? So here you can see like that this setting, lamp 2 and 3 are on, and lamp 5 is a false positive. Now we switch to another configuration with lamp 2, 3, and 4, and the system basically correctly identifies the lamps. The problem with these 2 smaller lamps is here that their contribution is relatively small, so that it is hard for the algorithm to actually figure out that as to whether they are on or off. Right, so this is something that you can actually now do. You can estimate the light setting on the fly and still being able to localize the camera. And here is the tracking on, like you can see the tracking also on the fly for this setting. And then can change the light setting on the fly and do some experiments about the localization accuracy, which is going to be on the next slide, I guess. Okay, give me a second. This is So basically, that what you can show then is that you're able to more accurately track a camera given these lighting adaptable maps and the ability to actually change the lighting conditions in your model, right? But the criticism that you might, or the argument that you might come up with is, but Wolfram, for now, you only used light sources, artificial light sources, and you basically didn't answer that question, how do you deal with sunlight and so on and so forth, right? And this is something that Michael worked on, over the past year, so that we are basically also able to estimate, to utilize the sun or the sunlight in order to perform this tracking. So the general idea is relatively similar. This is an extension of that what we have seen thus far. You're basically starting with the input mesh and the geometry and the reflectance, as we saw before, and then we basically pre-compute radiosities that come from the normalized sky, or the sky and the ground. So like light is typically also reflected by the ground of the environment and then comes through the window into your room. And these are those two are pre-computed. And then once you know what the time is and where you are, you can also determine the angle of the sun. And then once you know the pose of your room, you can basically calculate the contribution of the sunlight to your model, right? And then so you can use those to actually, and I mean, this needs to be updated like in a way lower frequency than the images that come in. And so basically the need to calculate a weighted sum of those three contributions now, and in order to basically generate the reference images. And then you can calculate the camera pose from this as before, and perform the and do pose estimates. And then here you can see like this in action. You basically on the left hand side, you see how the camera pose is estimated. The top right is the live image, and the bottom right is the reference image that is rendered from the model. And so you can here now see how the camera moves in the environment, and also see like different lighting conditions from the outside. And the interesting aspect now is that you can also like, it's just a generalization of that what we have seen before, that you can now utilize the shadows on the ground, for example, or on walls. And here, for example, this is interesting, or give me a second. It was interesting simply because I wanted to stop this video, but let me see so that I can actually get there. Should be around here, right? So you can here, for example, you can see a situation where you have, and this would be extremely hard for any camera-based tracking method that relies on features in or relies on features, because simply these shadows would be the only source for features in here. That would make it extremely hard to track these. And what you see here is mostly the shadows. But given that the model knows what the shadows would be, right, you can basically track the camera even in such situations. Right? So this is like where we can go with these techniques right now. So we can even make these models so sophisticated that we can accurately track systems under changing conditions, for example, or have these systems being robust to varying conditions, which is pretty good. Although, I mean, it is hard to do this also in an application like autonomous driving or cars, where you actually need to have a reliability that goes way beyond that what we can actually achieve, which is a reason why people actually went for these maps or HD maps in automated driving. And these HD maps can be either these 3D point clouds, right? And this is a map that Waymo uses, I guess, for ground removal. And that are feature-based maps, like where you basically see the edges of the road and the lane markings or poles for localization. And on the other hand, you do have maps like this down here, where you basically get the topology of an intersection and the data association of the traffic lights to the individual lanes. And things like that are like extremely hard to estimate, and also are like sources for potential failures. And this is a video on the top that Ryan Eustace once recorded in Ann Arbor. They basically can see like how the environment might change, like depending on different weather conditions. Right? And in fact, modeling like this is extremely difficult, and that is basically also the reason why it is very, very hard to go from automated driving level 4 to level 5, where we basically will be unable to record these maps, for the entire world. And the bottom image is basically a picture of the Waymo car getting stuck simply because there are like a couple of cones on the road where you can basically see that minor changes to that what the vehicle expected prevents the vehicle from actually executing its task. Right? So these vehicles are substantially dependent on these HD maps, and let it be with respect to the accuracy of these maps, or the fact that there's important information in these maps that they need to actually navigate at all. So, and this is like the discussion point I would like to get to slowly. So how can we deal with this, right? And obviously one option would be, okay, now that we know that maps might change, right? Why can't we have mechanisms to detect necessary changes? And this is a work that I've been doing with one of my students, David Pan, who's going to graduate next week, and where we basically look at this question, like how can we detect that the world has changed and that a map is no longer valid. And the idea there was to basically, or the motivation for this is that these mapping vehicles are extremely expensive, and the entire map creation process is so that what these companies, self-driving car companies have, like map operations teams, are extremely expensive. Right? So so building new maps or remapping both is extremely expensive. So we need to come up with more efficient solutions to this. And the idea that we had was basically utilizing the fleet for that purpose. Right? So many of the OEMs, they do have fleets of vehicles with cheap sensors that, and the question is, can't we use like all the cars in the world that have sensors like cameras and the GPS maybe to figure out as to whether the map has changed, as to so to actually ask the mapping vehicle to go there and recalculate the map. What you see here are heat maps of all the trajectories of BMWs on one day, and from that, like one would basically argue, okay, like that should be possible, right? It should be possible to at least map larger parts of the environment automatically, or check them automatically in order to figure out as to whether there are changes. Right? And in fact, what we wanted to do is to also use cameras for this purpose, to have cheap sensors that are installed in most of the vehicles. And here you can basically see the features that we looked at, which are basically the vehicle position, odometry measurements, GPS, lane marking observations, and road edge observations. And that what we used in this case were the lane markings, the positions, and the road edges, and there also the positions. And here you can see input data that we used from one of the test vehicles. And this is just the output of the lane detection system that they have by default in this vehicle, where you can basically see the alignment of all these features, right, or the perceptions of all these features that I spoke about, basically lane detections and or lane markings and road edge detections. Right? What you can do now is when you track a vehicle, right, then you can basically identify or look at the innovation between that what you expect from the HD map and that what the vehicle or the driver actually does. Right? And whenever you find a deviation from that, so it basically swerves to the left or to the right, then you would basically say, oh, there's a chance, or there's a potential that the map has changed. Right? And the point is that typically one traversal is not sufficient, and you want to actually do multiple traversals in order to justify that a mapping vehicle has to go there and then update the map. Right? And so that's what we basically did. We looked at particle filters to detect the innovation. We used bins along the road to actually see as to whether there is like a sufficiently large deviation from the predicted trajectory. And once that happened, right, we noted as to whether there's a change or not, yellow and green, or red and green. And then we basically learned the boosting algorithm AdaBoost for the classification as to whether this is a change or not. It's basically looking at these features and thresholds there. And yeah, here you can see in a typical result, a projection of that onto aerial imagery. So what you can basically see is whenever the green bar here is above the white disk, right, then the system says no change. And here you can basically see that like as we enter this construction area, like once we get the lanes go to the right, then it turns red and we get a strong vote for that something has changed over here. In Germany, when in construction zones, the lane markings are typically yellow, right? So if we had included this feature as well, right, then we could have even been more or better in this area over here, where basically the construction zone already begins. And can also see that from the learning curve that for single trace classification, you get substantially worse results than for multi-trace classification. So actually, this crowd labeling or this crowd data usage makes complete sense. But the question is still, like, let's assume we are able to build a map, right? And then you need some mechanism to figure out as to whether the map has, or the environment has changed, and as to whether the map has to be changed. Right? So if we were able to do this like in just one step, right? So the question arises immediately, do we actually really need SLAM then at that point, right? So from my perspective, the faster we are with reacting to changes, right, and making all these processes of generating maps more and more effective, which in fact you would start working on when you are like self-driving car company, simply because it is so expensive, right? So, and assume we are able to do this like extremely fast, right? Why do we need SLAM then? Why do we need this super accurate geometric representation, right? And I mean, you could also come up with this argument, right? We don't have this super accurate representation in our brain. Neither do we invert large matrices for calculating these maps, right? So, but we are still able to navigate around, and currently even better than self-driving cars. Right? But if you want to do this, right? If you really want to go away from SLAM on pre-computing maps and rather learn these maps on the fly, right, then all of a sudden things become really complicated, because then you need to reason about semantics, right? What is what, right? What belongs to what? Which traffic light belongs to which lane? Where are the lanes, right? So where did things move? And then you also need to infer road structure and intersection topology, for example. Right? And that are enormous challenges, and then they are extremely difficult to actually solve. But still, I think it is worth looking into these problems. And I want to talk about a few works that we have been doing in the past regarding this. So, for example, learning semantics and dynamics. So basically being able to track vehicles over time, which then will allow you to make better predictions, right? But also having semantics that tell you where the roads are, where the sidewalk is, and where the traffic lights are, for example. So these are all interesting aspects. And so basically the key question there is, like, once we get these LiDAR data, right, what is it that we see, and can we somehow provide this with more meaningful information than just the X, Y, Z coordinates of the individual points? And in fact, there is some work on this. So for example, one area to look into this context at is semantic segmentation, right? So the problem there is that you know what is what, but you don't have any idea what about instances, right? But then there's also instance segmentation, but there you don't get like information about, for example, roads. So amorphous regions are not segmented in a proper way, right? But if you combine those, right, then you end up having panoptic segmentation, where you get semantics about amorphous regions and instances. And this is super useful because you can then reason about all these instances that you have. And this is some work that we did 2 years ago, or started 2 years ago, where we actually came up with this efficient LPS system with a very, very dedicated network. So here, like the backbone consisting of a range encoder network, feature pyramid networks, proximity convolution module, and then like in the semantic hat, we are basically on the right hand side, we are basically doing the semantic hat and the instance hat, projecting that on the panoptic, or generating a panoptic prediction, and then projecting that back using a k-nearest neighbor approach on the original LiDAR point cloud. Right? And in this way, we are basically getting all the individual LiDAR points labeled. Right? Yeah, I will skip this and then briefly look at the data sets like semantic kitty and use scenes on which we evaluated this. Here you can basically see 2 examples. It was a little bit fast how we did this, or what the results are. And at that time, on the semantic kitty and use scenes, we were actually leading the leaderboard. This is now over, and which is good, right? So there are plenty of better approaches right now, but still there's something that I think it is worth being looked at and is important for future work. And here is this on the fly panoptic segmentation. And then again here, you can see now like consistent colors of the individual instances, which comes out if you just do semantic segmentation, then you would be inconsistent about the individual instances. Right. But the next step is like if you do this with images about like, or you look at panoptic segmentation, and again we see like in tracking settings that consecutive instances have different colors. Right? And so that's not really tracking. But on the other hand, there's bounding box tracking. So and the question is like, can we somehow combine those two to actually improve or to augment panoptic segmentation with the capability to track items. And this is called multi-object panoptic tracking. So where you basically have temporal instance IDs, and then you can from that calculate velocities and make proper predictions. And this is called multi-object panoptic tracking. So it was also a recent paper with Abhinav Valada's group here in Freiburg, former CMU student, by the way. Here you basically can see on the right hand side how that actually, what the idea is. We are basically interested in tracking these vehicles over time. Right? And again, that's always like when you throw machine learning in nowadays a deep network approach onto this, then end up be having like complex networks. And here you can see the architecture of this. It's basically built on the efficient PS architecture that you saw with 3 task specific heads for semantic segmentation, for instance segmentation, and for the tracking task. And then here, like the evaluation on the kitty data set, and on semantic, on virtual kitty 2 and semantic kitty. And so again, at that time, we were basically leading the leaderboard in terms of the panoptic quality. So yeah, and the same for vision and for LiDAR. Here you can see the vision-based approach. It is not 100% perfect, so the swan there now changes color, but getting there, and something like this would basically allow the system to automatically track items. And usually you have large groups of people working in car companies on the tracking task. And if you can replace this by just a network, then it's going to be way more effective. Right, and here you can see this also on the right-hand side on the LiDAR-based approach. The LiDAR-based approach, again, colors are consistent compared to segmentation only because you are basically doing tracking over time. And then it's also interesting when car comes to the intersection now in a second, and then you see these the other cars actually looking like tornadoes, but have them having the consistent color. Then or this in this video here, then by this you can actually see that the tracking process works properly. So you can see this here, the green car in front of our car, and as a red car passing by, and the pedestrian even crossing the road. So far about these type of questions. The other problem is, again, domain adaptation, and that what we are looking here is here was like the difference between day and nighttime, right? And of course, many approaches work on vision only, but using vision in nighttime imagery is extremely expensive. And so here, for example, is an approach, or it's extremely difficult. It's a standard semantic segmentation approach applied to a nighttime image. So, and that makes clear that it is going to be, at least we are behind with the ability of doing semantic segmentation in nighttime images. And yeah, here it's the same in the video. So the idea that we had was basically to look at thermal cameras, for which we think they have a lower domain gap between day and nighttime. So this is the thermal image for the very same scene. And the question now is like, how can we use these thermal cameras for this purpose of semantic segmentation? So the idea there was to basically use a multimodal heat net for doing exactly this task, and this multimodal heat net combines basically RGB and thermal imagery. So the approach is basically to have an RGB teacher used to learn the heat net in a way that the heat net generates similar outputs for day and nighttime images. Right? And once you do this, then the network is basically able to deal with RGB and thermal images at day and nighttime. Right? So this is the key idea. This is our car that we have in Freiburg with two RGB cameras and a thermal camera. And then even generated a data set that you can download. You can see some of these images in Freiburg. It's actually a pretty challenging data set. So we applied this to RGB and nighttime images, and then trained the heat net on this data, and for the test this, basically the ground truth, the test set that we are having. And what you can see here is that the RGB teacher, although pretty bad on the nighttime images, right? Our RGBT network performs pretty well and way better compared to the ground truth on the right-hand side. But what is also important to see here is that the RGB, if you drop the T component, so the thermal component of our RGB net, then it performs substantially better than the RGB teacher just on RGB nighttime images. Right? So you can basically use this approach in a way that you basically train the network using an expensive thermal camera, and then remove the thermal camera doing application and execute or perform just RGB-based semantic segmentation in challenging nighttime images. That's the interesting aspect of this approach. And here's a video at the very end of this talk before, but I've only just one more thing to show regarding so you can basically see that just despite the fact that it's so dark, you can still see the pedestrian. And the advantage is basically that you don't need to label RGB nighttime images, which is really, really complicated, like looking at dark pixels and trying to figure out what they actually mean. So at the very end, and it's going to take only 2 more minutes, is topology lane graph estimation, which is also a super relevant problem. not only for standard roads, but in particular also for intersections. And from my perspective, we are only at the beginning of this, but it is super important because it will provide the cars with the information about where they actually should go, right? And what are the lanes that the car is supposed to stay in. And right, so when you provide it with a map, then this is annotated, right? But if you throw away the map, then the car needs to infer this on the fly. And right, and here we ask the question: how can we learn HD map information from sensor data, and particularly from even standardized bird's eye view sensor data, so that we go through that representation to make it a little bit more independent of the specific sensor. So we use the graph RCNN for this purpose to basically then estimate a directional lane graph from different map layers calculated from different modalities. So, and the modalities that we're having were LiDAR, RGB, semantics, and observed card poses. And so you can see here like how our approach like inferred the individual lanes and directions for these snippets that you see here, and that it shows consistent results. And from my perspective, this is really promising. It is not as good as I had hoped for intersections, but it's a good starting point to look into this question of like, where are the individual lanes and in which directions do they go? Where can I actually go with the vehicle? So coming to the end, right? From my perspective, the key to robust robotic systems and cars that we have these days lies in these probabilistic approaches to SLAM and using maps. And the key problem now is like, if we rely to maps, then we are actually like faced with the problem of changes in the environment. And the only way to get away with this is to basically go away from like these pre-computed maps and maybe infer them on the fly. Right? And for that, we need a lot of machine learning. In fact, but if we are able to infer them on the fly, all these maps, then we maybe don't need SLAM anymore, right? So, and this is my my final statement here. And I thought that some of the people haven't seen the Exploding Probabilistic Robotics book, and this is why I add this slide over here. So if you really get rid of SLAM, then nobody really needs to read this book anymore. And then all you need is deep networks in the future. And that's something that I would like to ask and start discussing with you. Thanks for listening.
All right, thank you, Wolfram. This was really great. I especially like the lighting and being able to relight the scene. So I'll come back to that in a second. But since you're ending here on do we really need SLAM? So in some way, you would still be stitching together local information, unless I guess the extreme would be you look at a single image and you make decisions based on that. But you really probably would have to do something over a sequence of images over time, basically, to do more reasonable inference. And so that seems to go in the direction again of SLAM, maybe without loop closing. But if you want to do anything at a large scale and you don't have a prior map for self-driving, like a road network, then you would still need to even deal with loop closing.
Yeah.
What are your thoughts?
Yeah, I agree with you. But I mean, in the end, if you can do it from a single image, then there's no need for like, and you know, it's gonna happen, right? So people are going to say, maybe we are going to start with 100 frames, and then they will ask the question like, can we do it with 50 frames, right? And then like, so the limit is 0 frames or 1 frame. Let's put it that way. 0 would be blind.
I guess when I thought about this before, I thought, okay, if we are driving car, we really take a sequence of images into account, but we have some history. But I guess if you take a similar picture of an intersection, right, you can see all the we can see all the traffic lights and all the details, and so maybe that is sufficient.
in most cases, I mean, you still do have occlusions and so on, right? So in which case we also do make assumptions. So we sometimes trust the vehicle in front of us that it goes the right way, you know, and so we just follow that vehicle, and then yeah.
So there might need, yeah.
No, go ahead.
So there might need to be some more context, but it's maybe not necessarily geometric, but like behavior of things or predictions of what might happen next, more at a more abstract level.
Yeah. But it is still extremely difficult, I think, to realize a robotic system that doesn't use coordinates, right? So if you think about a robot navigating CMU and you want to send it to Michael K's office, you know, so when we use SLAM, then all we need to do is just click on the map, and then we get the position from there, and then we have all the machinery available, like path planning, collision avoidance, to just have the robot getting there with high reliability. But if you take all of this away, right, then it gets super complicated, and then maybe still the robot needs to have some sort of a memory, right? So if it gets lost, then it needs to basically be able to recover from this, right, back up to a place it has been to before, and things like that. Yeah.
Yeah, maybe for on streets, right? You have some topological map, you have the street network, but if you're in a building that's new to you, I guess you can still find an office based on room number at the end.
That's true.
So,
yeah, but this is also something that we add because humans are so bad in navigation, right, and remembering places.
Yeah, that was always my thinking. But if we can get the geometry, why not use it? And you can actually do something better that can take can be more efficient than what we can do.
Yeah.
For robot. Okay, that's an interesting discussion. So if anyone from the audience has a question here, feel free to raise hands or speak up here. Any of the people that are on Zoom. If not, then let me maybe come to the, oh, actually, let me start with another one. And that is, so where do you think things are going in the next 5 to 10 years? So if we go 10 years back, I think what we were maybe expecting, or some people were expecting, self-driving cars on the road. So they're clearly not there. I mean, to some degree, but they can't really be completely autonomous, and that's probably still a bit away. On the other hand, there has been tremendous progress in things that maybe were difficult to imagine 10 years ago. So where do you think we are in 10 years?
I mean, I think that SLAM almost has become a commodity, yeah, and that people now know how to do this. You still need like background there, but I think we will have like way more people using this technology, and we will see this in more and more applications. That is something I definitely believe. The other thing is that I think people should and probably will also work on these dynamic environments, map changes, automating change processes. I think this is something that I would like to see, at least see more in our conferences. And it is, however, difficult, like to come up with a benchmark for this, for example, right, where you basically do have some form of a dynamic environment, and then try to, like, what you would need to do is being able to estimate the success of the robot system, like navigating in this environment that changes over time. And this is an interesting question for me, also from a scientific point of view. Like, how can we do this, right? So would we phrase this as just like a reinforcement type of learning problem, or can we do this in a more simplistic way? And how do we measure this? And I think, like, once we start doing this, I think then we will also be increase the robustness of vehicles that are working in factory floors and in even self-driving cars, and make them more robust to changing environments. And yeah, I believe that the car companies or the big companies are already working on this, or maybe also have solutions for this, but I have no idea how good they are. And but I think that there's an opportunity for science to actually do something here and work on this entire, or have a more scientific approach to this lifelong mapping problem. So this is something that I would hope to see in the future. Making a prediction about as to whether this is going to happen is difficult.
Okay, great. I have some question on the reflectance, irradiance, etc. When you create these maps, so that you can later relight, how much effort is it to create? So can you just do the typical mapping where you just go through with the sensor quickly and later you can infer everything, or you have to actively control light, or
Michael, this is your turn.
Thank you, Wolfram, first of all, for featuring our work, and also thanks for the question. Yeah, so it's quite a bit of an effort to scan the room. So it's not just, you know, going with the camera around for like 30 seconds and then it's done. So it's more like, depending on how complex the geometry is, like maybe 10 minutes, because the more complete the more precise the models are, the better the simulation works in the end. Yeah, so there's again effort in first of all scanning the room, and second, then the processing also takes a bit of time, like, you know, generating the poses, generating the 3D mesh, and also the irradiance computation. You know, it needs ray tracing, so that also takes some time depending on your hardware. Yeah. So there is effort involved, definitely. But I mean, the map generation, the reflectance map generation was always thought to be like an offline process.
Mm-hmm. Yeah, yeah. But so no active lighting needed also.
Yeah, so I think one assumption is that at least during scene scanning, we expect the lighting to be static. So that's, I guess, one assumption here.
Yeah, okay, that's very reasonable. Yeah, this is actually easier than I thought. There's also a question from the audience, I guess on slide 63 specifically. There was a table on reflectance map and some value greater than 1. So
yeah, that was the where was this? In a second. It was the I guess the screen sharing got lost, but I will reshare in a second. Give me a moment.
So I guess the question here from audience
but I guess
how the values are calculated.
It's right that a reflectance should never be greater than 1. And the reason is essentially, I mean, it's an error, right? So we do it on real world data. And as I said, you know, you can expect perfect results if your data is perfect, if the reconstruction is perfect. In reality, it's typically not. So there's always a little bit of error. And I guess these values came from a white wall, where the ground truth reflectance should be like around a little bit lower than 1. But in this particular case, it's, yeah, it was over 1, but which is like an imprecision of the method.
Yeah, I guess that's expected. So
yeah, yeah. Sorry, the numbers are a little bit confusing in the bottom end. Yeah. And whenever, for weird reason, whenever I exit like presentation mode, then sharing stops. I have no clue why this is, but fine. Let's do it, let you know.
Okay, yeah, the results, I mean, were very impressive here for being able to switch on and off lights. And it's expected that in the estimation rate, the numbers cannot be perfect. So it's actually good to see that. Okay, let me see, what else do we have? I guess there was a question regarding HD maps. Do you know if there are any encoding methods for SLAM? As big HD maps take a lot of storage and thus are expensive.
Yeah. I mean, there's different ways of HD maps, right? So some companies use actually 3D point clouds, right? That's like, and others use like feature-based representations, which are way more effective and require way less space. So, for example, if you think about just storing the lane markings, and it's basically lines that can be represented by 2 points, or like poles, for example, it's also like 2 points, nothing more, right? And then also the borders of the road are nothing else but like simply linear sequences of polylines, so to say, right? So this can be extremely compact, right? Compared to point clouds, which are super expensive, but there you do have like a more limited amount of pre-processing that is needed. Right? So yeah, then you can do basically all kinds of compressions, but I do not have any idea what good compressions would be for this and which one to use. I mean, in the end, you do need to do particularly these point clouds. What you want to do there is raycasting, right? In order to figure out whether your actual measurement corresponds to the predicted measurement. And for that, you need to calculate perform raycasting in the network, in the map, to basically understand how far you can go until you hit the first object. And for this, you need to have actually very, very compact representation. And compressing this is something I don't know how to do this and how to do this still efficiently, but it would be an interesting topic maybe.
Cool, thanks. I have another comment from the audience here. Thanks for the great talk. Are current approaches in visual SLAM good enough to work in unstructured environments like forests? Can you share your perspective on improving the same?
I mean, I think that unstructured environments are sometimes better than structured ones, because we tend to have like uniformly colored walls, which make it extremely difficult to track the camera. And you have many more features in these unstructured environments. On the other hand, I mean, creating a map of a jungle is close to impossible, I would say, right? So because all this is like continuously in motion, right? And finding stable features there is extremely hard. I think tracking would be easier, but global localization or loop closure can be arbitrarily hard, I think. Yeah, and I'm not aware of any approaches that do this in a convincing way. There have been robots doing this in outdoor settings, so people actually on dirt roads, not in the forest itself, but yeah, would be worth looking at. I think it's an interesting question. Thanks.
And then another question in a similar direction. Maybe get to know what's Professor Burgard's take on direct versus sparse approaches to SLAM in the context of deep learning.
Once again, like direct versus
sparse approaches.
So you mean in
SLAM.
Visual SLAM? Yeah, that is a good question. I mean, these dense approaches are usually like also pretty impressive, and I don't have a preference there. I just can't tell, and I think both have like their advantages and disadvantages, and I wouldn't say one is inherently better than the other, right? Because these sparse approaches usually require features, and then you fail in featureless environments. And these dense approaches do not rely on features, but then they sometimes are worse than when there are features around that you could easily exploit. Right? So, I mean, it is some sort of a heuristic, and then for every heuristic, you have counterexamples typically.
So I guess really depends on the specific environment, on the sensors that are used. And
yeah.
Okay. Yeah. Thank you very much again for your talk, Wolfram.
Was a pleasure.
All right. Are there any more questions from our live audience here? If not, then okay, great. Thank you.